Hello, welcome back. This is Samuel Ambrose Onen. I would like to take you back to the previous video that we have covered concerning the origin of the file system, if you like, but we have narrowed it down to the level of bits, the binary system, because as you know, binary system define the digital data that we consume on a daily basis. And that, my friend, is the origin of everything that we do digitally, because computer system is based on binary system, which is all about bits, the strings or the streams of zeros and ones that are processed by the processor. So in the previous video, we took a look at, at the bits, and we have seen some of the fallacies, that people look at bits as being a storage unit instead of taking it as the actual state of the system or the data that the system actually processes. Also, we looked at it as being 8 bits, which is also another form of, I would not say a fallacy, but it is very closely, because when somebody describes byte as being 8 bits, you know, is not enough, because as we know, all these are standards for communication. For example, the ASCII, which is the American Standard Code for Information Interchange, define byte as a digital standard for encoding a character, one character, and that character must contain 8 bits, or we need 8 bits to represent one character. And that is all about byte. So byte is a standard for encoding a character in form of 8 bits digitally in the system. And we look at the fallacies as being 8 bits only, because if you look at the internet, you will see that most of the description or definition of byte, people will say byte is 8 bits. They ignore the other part, the most important part of it, as being a standard for encoding a character using 8 bits. So 8 bits is really the content of 1 byte. And when we get that 8 bit plus 2 extra bits to make 10 bits and raise it to the power of the binary system base 2, we get what is called kilobyte. But there's a lot of fallacies there that people think of kilobyte as 1000 bytes, which is not very true, but it's close to the truth. It's close to being true. Because some people argue that because a byte is only 2.4% higher than 1000, therefore, kilobyte is 1024, which is only 2.4% higher than 1000. Therefore, it is prudent to say that a kilobyte is equal to 1000 bytes, which to me is not correct. We have to be specific in science. Science is not a subjective subject. It is an objective subject. Therefore, I'm happy to correct you that a kilobyte is actually 1024 bytes, which is found from 10 bits, of the digital state of the system, or the binary digits. We need 10 bits because 2 extra bits on top of 8 actually are used to to account for other, empty spaces, the space just before a character and after character. We need 2 bits to account for those 2 spaces. And those 2 bits, when you add it to the 8 bits, which represent the actual character, it gives us 10 bits. And when you raise that 10 bits to the power of 2, my friend, that's why we get 1024 bytes to represent a kilobyte. So that is all about the byte, and that's what I wanted you to take home from the previous video, and wanted you to know how that 1024 is found, and the reason for using the 10 bits or the extra 2 bits to add on the 8 bits in a byte to form a kilobyte, which is 1024, is just because we want to account for the extra space between the space before a character and the space after a character. You can think of it in terms of asynchronous communication, whereby the data is sent, you know, can be acknowledged by 1 bit, and the data received can also be acknowledged by an extra bit. That's another way of looking at the extra 2 bits that are required to make 10 bits in order to represent a kilobyte. So from here, everything will be the multiple of this bit, this kilobyte, in order to create another or more space or spaces that we need in the file system. So kilobyte is the smallest amount of space, if you like, that a computer can have. You know, the smallest space of memory. I mean, the smallest size of memory that a computer that we can have for a computer, because that will take up to around about a page of characters, because 8 bits is only one character. So if we have 1024 bits, that will give us almost like a page of character, and that produces, a complete page of character. Just think of it like a page of your book. Just one page is 1 kilobyte. And that is the smallest size of memory that we can have for a computer. And the processor fetches data from the memory in 8 bits, and then it has to process them bit by bit. So just imagine like you have 1 kilobyte or 1 gigabyte. The processor will not actually process that kilobyte or gigabyte like that. It will fetch a byte, and then that byte is just like 8 bits, and then it will go inside the byte and then run through each of the bits which are there inside the byte one by one to interpret what it means, and then fetch another one like that in 8 bits. So the rate at which the processor fetches the bit is called the hertz. That's why we have like a processor of a size of 2 gigahertz or 1 gigahertz or 1.5 gigahertz. That means in one second it fetches 2.5 billions of bits. That's why he says when you have a processor of 2.5 gigahertz, that's pretty good processor which runs very fast, because it actually fetches these bits from the memory, I mean, these 8 bits, and processes it, you know, at the speed of 2.5 gigahertz, for example. That means in 1 second, the processor can fetch 2.5 billions of bits, you know, in 1 second. How fast is that? How cool is that? So those bits are processed in real time. That's why processor works faster than human brain. So, my friend, that's the summary I wanted you to grab. So, in next video, we're going to look at these into details. So, thank you for viewing. I hope this video has been informative.